Okay, so good morning, good afternoon, or good evening, everyone, depending on where you are joining from. I'm Koji Yamashita, the moderator of today's webinar from UC Riverside. Welcome to the Archway PES Foothill section. Our Foothill section spans a wide geographical area stretching from West Covina to the eastern edge of California and from Temecula to Baker. And today we are honored to welcome a distinguished guest from the industry, Dr. Vinay Sewdien from the Netherlands, a respected expert in the power sector. Thank you for joining us, Vinay. And before we begin the presentation, allow me to briefly introduce our speaker. Dr. Vinay Sewdien is a seasoned expert in electrical power engineering, holding degrees from Anton de Kom University of surname with a Bachelor's of Science, KU Leuven Catholic University of Leuven with a Master of Science, cum laude, and Delft University of Technology, where he earned his Doctor of Philosophy, cum laude. He spent over 8 years of tenure, beginning as an international trainee and later serving as policy advisor from system operations. During this time, he was actively involved with SIGRE, serving as Secretary of Study Committee C2, meaning Power System Control and Operation, and as a member of the Electra Editorial Board in 2021 through 2023. And then Dr. Sewdien has continued to leading the energy transition through key roles at Shell and more recently as EMEA Power Transmission System expert at Microsoft. He also chairs the Education for Development Foundation, supporting educational initiatives since 2021. So Vinay, the floor is yours.
Thank you. Thank you very much, Koji. Welcome all. And thank you for having me. Thank you for the kind introduction. So what I'd like to do today is discuss with you one of the main works I did a few years ago on the energy transition and how the energy transition is actually shaping the way we operate our power system. So what we're going to talk about today is the impact of increasing levels of renewable energy sources on the way we operate the electrical power system. Once we have, I mean, what I'll do is I'll walk you through, you know, the work we did on operational challenges, and then speak a little bit about, you know, what are some of the activities we need to do to enable more power electronics interface devices. And then I'll just share some relevant publications that could be interesting as a additional references to read. Now, power electronics interface devices, those are all sorts of equipment, electrical devices that are interfaced with power electronics to the grid. So these can be your renewable generation assets. These can be your demand facilities, such as data centers. It can be interconnectors like HVDC. So everything that's related, that's interfaced with power electronics, we call power electronics interface devices. Now, if we look at what's happening in the globally, right, with regards to the energy transition, we'll see that there are three main contributing factors that, let's say, that shape the energy transition. The first one, it's a no-brainer, it's a changing generation mix. So what do we mean with the changing energy mix? What you can see here is a figure with 4 geographical areas. And what you see here is the share of wind and solar PV compared to fossil fuels, so coal and natural gas generation in Ireland, United Kingdom, Denmark, and Australia over the last 2 or 3 decades. What you can see here is in all 4 regions, and again, it's only until 2017, so the numbers are much higher now, but what you can see here is in all 4 regions, the level of power electronics generation is increasing quite rapidly. Now, here in Australia, it might seem like it's not a lot, but in one of the regions in Australia, namely in South Australia, the penetration of renewable energy is more than 100%, meaning that they export renewable energy to outside of that South Australian power grid. What you can see here now is the situation in Ireland. In Ireland, the system operator is called EirGrid, and what they have shown here is a measurement or basically an overview of the level of power electronics in the power system. This blue line here, the dotted line, that represents the maximum electrical renewable energy that the system can handle. And you can see a yellow line here. The rest is not really important. You can see the yellow line here. That is what they call the system non-synchronous penetration index. It essentially means all the renewable generation plus HVDC imports. What's interesting to see is that back in 2019 already, they were hitting their limit for a few hours already. Back then, the limit was at 65%. Now it's of course higher, but in 2019, they were already hitting that 65% limit. Why do they have this limit? They have this limit to ensure that the system can operate in a stable way. If you have too much renewable generation in your power system, the system is much more prone to have outages and instabilities. So this is the first let's say contributing factor, or at least defining factor of the energy transition. And this is true across the world. Of course, that change in renewable generation, the speed with which renewable generation is taking off is different in different parts of the world. But essentially, in most regions, you can see that there is an increasing level of renewables penetrating the power system. The second topic, the second defining factor is that regulation in the context of the power system is evolving very, very slowly. What I mean with this is that if you get all the generation and demand into your power system, you need to have regulation that govern how they should behave, for example. Now, that is going rather slowly, and that is causing some of the issues that we'll discuss today. Finally, there is quite some difficulty in realizing new transmission assets, so in building new overhead infrastructure, so transmission lines, distribution lines. It's quite difficult to build it in time. Just to give you an example, in United States and also in Europe, it takes approximately between 9 and 15 years to build new transmission assets. And just to put that in perspective, if you want to build a new offshore wind farm, it should connect to the onshore transmission system for which you need transmission assets. That only takes approximately 5 to 6 years. So there's quite a big mismatch between how fast generation and demand they get online versus how long it takes to build new assets that are needed to transport that electrical energy. Now, when you combine these observations and you group them together and you assess it, you'll see that the energy transition is posing important operational challenges for system operators. So in the way they should operate the power system. And the main question that we try to answer, or that we need to answer here, is that assuming the level of reliability and affordability of the electricity system that we have today, how should we operate the future power system, which is characterized with low inertia, for example? And before we can answer how we should operate this, one of the fundamental issues that we need to address is, what are the challenges, right? What are the specific challenges that relate to this energy transition, or that are caused by the energy transition and that need to be addressed in order for us to maintain the same level of operational reliability and affordability for the future power system? So in order to answer this question, what I did a few years ago is I led a international consortium of many system operators throughout the world. So you had system operators from the United States, from Canada, from various countries in Europe, Asia Pacific. So there's quite a well-represented group of system operators. But also we had equipment manufacturers like Siemens Energy on board, or Hitachi Energy. Now, the goal of this consortium was to investigate exactly this question. So what are the challenges and how can equipment manufacturers try to modify their equipment to help solve these issues? Those of you that joined a bit before before the meeting started, you heard Koji and myself talking about grid forming. Now, grid forming is one of the solutions that these manufacturers are trying to develop, and that would address some of these challenges. So what are these challenges? So we had quite a lot of work was done on this, and we grouped, and I think we got more than 30 challenges out of the interactions we had and all the work we did, and we group them in three main categories. The first one is the challenges that relate to the new behavior of the power system. The second one would be challenges that relate to a new operation of the power system. And the third one is challenges related to lack of voltage and frequency support. You know, for a power system to work reliably, you need to have an as much as possible stable frequency and an as much as possible a voltage that's close to its nominal value. So 100% of that value. The frequency in United States is 60 hertz. So you want to make sure that, you know, at all times you are at 60 or very close to 60 hertz. So the challenges that we found, we grouped across these three categories. Let's look into them. So when we talk about the new behavior of the power system, this deals with issues that make the system behave in a different way than we have been used to. So this means, for example, that your frequency behavior of your power system is changing. You're getting different harmonic behavior, you're getting resonances, and this happens, for example, due to more and more underground cables, right? Then when we look at the second part, that is the new operation of the power system, this deals more with, because that system is changing, how should we operate the system in a way that we can still maintain reliability? And one example is that because the system is changing, phenomena happen so fast that grid operators, they may not be able to observe and act on it. So essentially what we mean here is that we need more automatic control actions that help to deal with such fast phenomena. And then the third one is you know, the lack of voltage and frequency support, and this deals all with the stability of the power system. So when we talk about stability of the power system, it essentially means the ability of that grid, right, to remain stable when a disturbance happens. So imagine a power plant shuts down, or a demand facility like a data center is going out, right? The ability of that grid, right, to maintain operations, so to remain stable, everything of that falls under this category. Okay, now let's look at some specific examples of these issues that we found. Again, this is just as a visualization. I'm going to explain each and every one of them. So when we look at the new behavior of the power system, right? There are a few things that we can see. One is, because of the lack of conventional generation, so synchronous machines, the system strength, so the way the stiffness of the power system is changing. And that can that can lead to various other challenges, such as the fact that your voltage in your system is going down much more rapidly, or your protection devices, they don't operate as they should. Another issue here is that we get new power oscillations in the power system, or we get new resonances in the power system. So there are various challenges that need to be addressed, which are caused by the changes that we see in the grid. Now, when we look at the second category, that is looking at how should we operate the power system in a different way. And there are various things that are very important here. One of them is new operator skills. And one of the skills that these days is very, let's say, top of mind is, are system operators skilled to use artificial intelligence like Copilot or ChatGPT? How can they work with that? Other challenges include, observability and controllability of RES, renewable energy sources. Observability means, can the system operator actually see, measure, and observe all the renewable assets that are in the system? That's quite a big challenge these days. And the related challenge to that is the controllability. So once they can see the assets in their SCADA system in the control room, do they have the option to actually control that renewable energy source? Other challenge relate to the coordination between utilities, right? So in the case of the US, it would be the coordination between, let's say, MISO and PJM. Or to what extent can they are they able to work together to coordinate all different operational actions? Now, when we look at the lack of voltage and frequency support, here are also some interesting challenges. They relate to the decreasing inertia. So inertia in the system is mainly in the power system is mainly provided by your conventional generation. So that would be your oil and your diesel, coal and gas-fired power plants. It would be your nuclear energy, your hydropower. So the synchronously connected generation to your power system. Now, of course, if you have more and more renewable generation in your system, these conventional units, they get displaced. And with that, there's a decrease in inertia, which causes all sorts of additional challenges related to frequency stability. Another challenge is that the renewable energy sources, let's take solar PV, for example. They start to generate electrical energy, I don't know, around 7:30 a.m., and then they go down around 5:30 p.m. So going up and down, right, when the sun starts to shine and it goes down, there's a huge need for ramp. So what you can see here, another issue is, how do you manage these ramps? And I have an example of, I think, called California, which I'll show it in a minute. So these are various challenges that you can see in the power system. And some of them are already observable, other ones we will observe. And again, I know it's a lot of these challenges that need to be addressed, but I think as electrical engineers, this should be great news, because it means that, the value that we can bring as electrical engineers is increasing by every day, right? So it's quite an exciting time to be an electrical engineer. I graduated myself in more than 10 years, almost 13 years ago. And the amount of challenges that, new challenges that you see, they keep on increasing. So it's very, very dynamic. And I think really nice to be an engineer, electrical engineer in this time. What I want to do next is I want to walk you through some of the examples, and they are all examples that were actually observed by utilities throughout the world. So the first one is an example of the Netherlands, of Ireland in Europe. And this is called voltage dip induced frequency dip. So essentially what it means is that because there is a voltage dip in the system, in the power system, your frequency is following that behavior and is causing a dip, which then again can cause frequency stability issues. So what's the issue here? You can see the blue line here is the voltage, and the green line is the active power. So Ireland has a lot of, I think, has a lot of renewable, a lot of wind generation, and I mean, I showed a figure before where they were hitting this 65% system non-synchronous penetration index. So what happens in Ireland is that, or what happened, this is a true case, is that at a certain point in time, there was a fault in the system. And you know, when there is a short circuit in the system, your voltage goes down. When the voltage went down, there are certain wind farms, that's mainly the type 3 wind farms, as a certain type of, there are 4 types of wind turbines. This is one specifically for a type 3 doubly fed induction generator. What it sensed is that the voltage went down, and as a result, immediately it discharged its own load. Now, you know, when you have a fault and your protection activates, you can see that the voltage almost instantaneously go back to the nominal voltage. However, because it's a wind turbine, there is a certain ramp up before that wind turbine goes back to its nominal value. What's the issue here? The issue here is that the dip in active power happened instantaneously, but then there's a slow ramp up, and this behavior, right, this active power recovery is leading to a the active power recovery is leading to a deficit in the let's say in the electrical energy, which may cause frequency stability problem. And this is something that was really observed in Ireland. In the meantime, there are various solutions that have been implemented, again, by electrical engineers looking at the issue in more detail and then investigating it and providing mitigation measures. The second example, which relate as well to the category of new behavior of the power system, is the resonances. You know, when you have resonances in your power system and if it's triggered, you get all sorts of harmonic currents in your power system. Or oscillations, I should say, not harmonic. You get oscillations in your power system. It's not the harmonics, apologies. So whenever that harmonic frequency is triggered, you get an oscillation at that frequency. The nominal frequency of power system in US is 60 Hertz. In continental Europe, it's 50 Hertz. So what you can see here, focus on the red lines. That is the normal harmonic impedance of a part of the system, of the power system. Now, there were plans in the Netherlands to connect a wind farm. In order to connect that wind farm, there was a need to upgrade the power system, and additional investments would require an underground high voltage AC cable. You know, high voltage AC cables are capacitive. So the system operator did a study, and they realized that in order for them to make to connect the wind farm, they need to have that a cable connected, and you can see that the resonance frequency, it shifts from approximately the 4th harmonic up to the 2nd harmonic. So it brings it closer to its nominal value. This means that the system operator now needs to develop or design a filter to make sure that, you know, this harmonic, the 2nd harmonic, is suppressed. Because again, as I mentioned, when it's triggered, you'll get an oscillation at the 2nd harmonic. It's something that you, of course, want to prevent. Now, let's look at operation. So I gave you 2 examples of the new behavior of the power system. Let's now look at the new operation of the power system. And you know, when we talked about operation, we discussed congestion, we discussed the new skills needed, but I want to shed some light on congestion specifically. What you see here, maybe the left figure is not that relevant. Let's focus on the right figure. What you can see here is that the increase in renewable energy, right? So on the x-axis, you have the energy penetration of renewables. And on the y-axis, you have the curtailment rate. So curtailment refers to the system operator actively reducing the output of the generation because of system security issues. So if the system operator would not have curtailed the generation, you would have overloads on your line, so protection would be activated. So what the system what they found both in the UK and in Germany. So the yellow line is for Germany, the blue line is for for the Britain. What you can see here is that the more renewable energy you get into the system, the more you have to curtail. So the more you have to reduce its output at a certain point in time. And this is because renewable energy is not dispatchable as such. So you need to make sure that if you want to have a system with a lot of close to, let's say, net zero, you need to have a lot of renewable energy, renewable capacity. So if you have a demand of 10 gigawatt, your renewable capacity needs to be much more than 10 gigawatt, right? Because of 1 gigawatt of renewable generation or renewable capacity of a wind farm, it does not equal 1 gigawatt of electrical production because of wind speeds being lower than the nominal value and various other reasons. So as a result, they normally overplant the renewable generation facilities, and you have to curtail them much more, which is of course expensive for the society. The issue here is also that if you curtail the renewable generation, at other instances you will need additional generation because there's not sufficient renewables. So you would have to you would need other generation facilities to provide that electrical energy. So it makes the way you operate the power system a bit more difficult. Now, if you look at the lack of voltage and frequency support, what you can see here is the frequency measurements over a 100, over the 10-hour time frame. You can see the hour 90 up to 100. On the y-axis, you have the frequency. As I mentioned before, the nominal frequency in continental Europe is 50 hertz. So ideally, your frequency would be continuously here. So what you can see on the screen is the measured frequency in the Netherlands, but the frequency is approximately everywhere the same in a synchronous area. So what you can see here is that at every hour, you can see that the frequency shows a dip, right? It's quite a big dip compared to the other instances. And this happens because in the Netherlands and Europe, you have the operations, the dispatch is different every single hour. So every single hour, because of change in the dispatch of generation, you can see these big dips. However, if we would have sufficiently large inertial response, so a sufficiently large synchronous machines, this would not be this steep. And you can imagine with more and more renewables coming in, these dips are getting larger and larger and larger. So this is something that requires a lot of, let's say, engineering to mitigate this. So this is an example on the frequency. Now, let's look now an example. Let's look at an example for the reactive power. So the reactive power is needed to manage the voltage in the power system. What you can see here in the figure is the reactive power demand in the UK grid for a long period of time. It's up from 2015 up to 2016. And on the y-axis, you can see the reactive power demand, where positive means the system is inductive, so it consumes reactive power, and negative means it's capacitive, meaning it produces, generates reactive power. You can see here that over time, the behavior of the UK grid is changed. And there are various reasons for it. I mean, one of the reasons is that when people install solar panels, right, the electrical loading on transmission lines, they reduce. As they reduce below something called a surge impedance loading, your transmission system, your transmission lines, they change behavior from being inductive to being capacitive. So that's one of the explanations. The other explanation is that there's more and more capacitive demand in your power system. More and more power electronics, essentially. So you can see that the way that the power system here needs to be managed is different. First, it was inductive. Now it's being more and more capacitive. And this is a growing concern in UK. And then next, I want to show you a figure of California. This is from CAISO, the utility, the independent system operator of California. We discussed earlier the ramp management. So what you can see here is the time. So 12 a.m. to 9 p.m. of a day, of a spring day. And on the y-axis, you have the load, so your demand. In California, there's a lot of solar energy. A lot of households, they do have residential PV. So what happens is this is the demand, the load profile that the system operator sees, or CAISO sees. In 2012, you can see that, you know, this is the profile, and then it follows this line, and then, you know, there's a certain need of ramp. But then look at 2013, this dip is becoming larger. And up to 2020, because at 6, 7 a.m., the sun starts to shine, the solar energy is starting to generate electrical energy, which what you will see, what the system operators see in their control room is a reduction in demand, right? Because it's generated and consumed at the same level. So they see a rapid decline in the generation, in their demand. And then in the afternoon, they see the opposite happening. But then what happens here is two things. First of all, the sun is going down, but also people are getting home. So they're switching on their air conditioning, they're switching on their lot of appliances. So there's a steep increase. So these things, they're called, they identify, or they inform the ramp management needs that a system operator has. And the more we look into the future, the more we see that these things they get more and more steep. I think, was it last year that this curve was even very, very close to zero. So you can see this becomes very tricky for the system operator, to manage. And then lastly, in terms of examples, this is again a case of Ireland, where we discussed excessive frequency deviation. So when you have a power system with a lot of inertia, with a lot of synchronous machines, if there is a small deviation in generation or in demand, your frequency remains at the nominal value. In Ireland, that's 50 hertz. So what they did in Ireland is they did a study where they looked at two systems, one with 60% of renewable generation, the other one with 80% of renewable generation. And what they did is they introduced a similar disturbance. So for that same disturbance, you can see that in a system with 80% renewables, that frequency deviation is almost double. So you can see here it's a 4 hertz, 40 millihertz deviation, so, right? 50.04, and here is a 50 millihertz deviation. You can see here it's a 100 millihertz deviation, and here a 90 millihertz deviation. So you can see that under the same conditions, except for 80% renewables in the system, your system is showing more and more frequency deviations. So it's, again, this can lead to frequency stability issues. It can lead to disruptions in the quality of the supply of the power system. So you can see there are a lot of issues that need to be resolved. And again, it's a great time to be an electrical engineer. Just pick one or two of these topics, and I think you can work your entire career on solving them and providing really, really good value. Now, we have seen a lot of these issues, we have seen a lot of these challenges, right? But at the same time, how do we enable more power electronics in the system? So how do we enable more renewable generation, more HVDC converters, more and more demand, like our laptops, data centers, you name it? The first thing is, I think, both system operators, society, we need to be aware that power electronics, they are not only a threat, but they can also, you know, be a solution to many of the issues we see in the system. And there are a lot of examples which I haven't touched upon, but where you can see that power electronics, they're actually part of the problem, right? They can help and provide various mitigation solutions for not only one, but multiple of these challenges. And I will touch upon one of the publications that I would really recommend you to have a look at. Now, what steps should be taken, to make sure that these opportunities that there are with power electronics, they can be turned into real benefits? The first one, as I mentioned, right, making sure that we understand that these devices can bring substantial benefits. There's a lot of collaboration required between utilities and vendors, because utilities need to be very clear on what issue do they have that needs to be resolved. It needs to be in such a way that vendors understand the language, they have a technical description, because once they know that the utility has, I don't know, a excessive frequency deviation issue, they know how to develop solutions for that. The other thing is that there is a big need for standardization. You can not for every single solution you want or issue you want to develop a customized solution. You want to standardize as much as possible to make sure that the delivery timelines and the lead times in providing these solutions are not too long. And of course, these power electronic devices that can bring the solutions, they need to be performance improvement. So you heard Coach talking about grid forming control. It's a new type of control philosophy that can bring significant value, but somehow we are still in the piloting phase. There needs to be a lot of work that needs to be done to scale that up to commercialized solution. And what I think is interesting for this group is a few publications. So you heard me talk about a lot of these operational challenges. I would really like to refer you to this this paper called System Operational Challenges from the Energy Transition. It's the paper I co-authored as part of the convener of that consortium, that working group. It's freely accessible, so it describes all of these issues in much more detail, and it gives also the mitigation solutions that I discussed briefly, right? It discusses about these solutions and what type of power electronics device can mitigate some of these solutions. And then these are three other references. The first one is a technical brochure which describes in much more detail the paper that I referred to. Then if you want to take a step back and look at how would this future system be operated or designed, this is a book that I had the pleasure to co-author, but it was written by Sigre, and it looks at all aspects of the future power system, from transformers, protection, technical performance, operations, environment. So it's quite a good reference to look at various aspects of the future power system. And then, of course, the issues that we see, we have to resolve them. And that is one of the books that was published by some experts. Is called Flexible AC Transmission System Facts. They are normally power electronics interface devices that provide a wide sort of solutions to many of the problems that we can see. I think that brings me to the end of my presentation, and I think I would now, Koji, give the word back to you to moderate the session of questions.
Thank you for the nice presentation, Vinay. Very informative. So the folks, if you have questions, please utilize the chat window, because now today we have like close to 30 participants in total. So if you have questions, just type your question or comments on chat window. Then the speaker Vinay can see it later on. But in the meantime, so you mentioned that so the inverter-based resources can induce like I don't know which slide. I think in like a slide number 3 or 4, you showed like a low frequency oscillation caused by inverter-based resources. But for my understanding, the frequency must be relatively higher, much higher than the inter-area oscillations caused by renewable energy resources. So my question is, why do we use low frequency in your slide? So what is the like the frequency range of the oscillations?
So that's a good question, Koji. So normally, if you look at inverter-based generation, right, you're right, they have a rather, under normal conditions, they would have a rather high oscillation frequency. However, there are two instances where when you will have a low frequency oscillation. The first one is in the case of a doubly fed induction generator combined with a series capacitor. So that is the case that you had in ERCOT, in the Texas grid. The oscillation frequency can be anything from, on a 60 hertz grid, I think it would be anything between 15 and 50 hertz, depending on the LC configuration. And then the second low frequency oscillation that can happen, or subsynchronous oscillation that can happen, is in the case when you have a VSC, a type 4 wind farm, or HVDC converter, or a BESS that's connected in a weak grid. So that is a short circuit grid with a short circuit ratio of less than 2. And then depending on the control, if you have a active power control, or you have a VDC, the DC voltage control, that frequency can be anywhere between more to the lower end, maybe between again, this is now in a 50 hertz configuration, it would be around 4 or 5 hertz to 15 hertz. And if you have the DC link control, I think it is between 10 to 30 hertz, or yeah, those are two of the examples.
I see. Good to know this. And also, yes, especially in the US, we are expecting like increasing demand from, for example, like GPU servers in the future, because we're gonna use more like the GPU servers for AI technologies.
Correct.
And then, so, if we consider the increasing demand each year, that is actually huge. And then, as you have already mentioned, it's not easy to build a new power stations right away. It takes a while, probably years, to build power stations. And I don't think we can cope with, we can cover the significant increase in demand, like the gigawatt scale per year, using renewable energy resources only. So I think we should still rely on like a conventional, like thermal power units. But on the other hand, we have like, we have to reduce the CO2 emission as much as possible. So in European countries, I think you're also, increasing number of like the GPU servers as well as EVs, and how you can cope with the increasing demand in the future. I understand that the building transmission line is really important to transmit the energy, but we also need the energy resources itself.
That's a very good point, Koji. And I think what is happening in Europe is at both at country level as well as at European level, an energy resource adequacy is performed every year, at least once. And that looks at the next season, it looks at the next 5 years, it looks at the next decade, and it takes into account all the scenarios which are looking at demand increase, right? And then they look at, considering the demand increase, is there sufficient electrical energy to meet that demand? Then there are two types of solutions. One is, depending on the amount of, let's say, energy deficit, right? The market will automatically react on that, because if they see that for 500 hours per year, there's quite a high premium that you would get to provide that energy, it would incentivize them to build new plants. That can be various sources, can still be renewable, of course. The other aspect is flexibility. That's a major thing currently. So system operators are also very much focusing and incentivizing flexibility. We're not there yet. There's still a lot of work that needs to be done in both understanding flexibility as well as providing adequate regulation and framework to enable that. But what you see is that if you have a certain point in time that the energy demand would be higher than your generation in the entire system, you get a flexibility product where system operators can ask and pay facilities to reduce that demand and then meet the balance.
I see. Can you see the chat window? There is one question from audience today.
Yes, reactive power is reverse flow. Please describe more. I do not get the question, Koji.
The reverse flow. Reactive power is reverse flow. I don't get it.
Okay, I can tell you. Actually, yeah. Can you hear me?
Yes.
Yeah, reverse flow actually maybe a little bit confusing, but one of your slides you showed, you mentioned also the inductive then capacitive, same thing. So it is go the opposite way. So why? Can you please describe a little bit why and why the system support it?
So this is that's a good question, Ahmed. So if you look at the system normally, right, how the system operator looks at their power system, how they operate the power system, they have at every substation they have measurement devices, right, and they look at how does the system in general, what is its reactive power state, let me put it this way. And then if you look at most power systems up to now, they have been inductive. A transmission line is essentially a coil, it's an inductor, and therefore if it is loaded above its surge impedance loading, it will show an inductive behavior. Now, there are two things happening with that. The first one is the demand, because of all the solar on rooftop and everywhere else, right? And you can see that the flow through the lines, right? The flow through the transmission lines, they are decreasing. The impact of that is that when you're loading your current through your line is below something called surge impedance loading, your transmission line becomes capacitive. It's nature, right? Its nature changes, and therefore it starts to generate that reactive power. So that's one. The second thing is the demand itself. The type of demand, it's becoming more and more power electronics interfaced, which means power electronics interface devices normally are capacitive because they have a lot of power electronics in them, right? So a lot of capacitance in them. So that can be all sorts of devices that you can have at home, larger IT load, like Koji mentioned. All those things are making the system a bit more capacitive. So the system cannot, it's not a question of how does the system allow it, it's more that is the nature at the individual substations that you can see that its demand for reactive power is decreasing and now switching even to being more capacitive. The result, how do the system operator deal with it? I'll give you an example of Spain. In Spain at night, in Spain, what happens is that they have a lot of solar generation. So during the day, there is a lot of transfer going on in the lines. So the lines are heavily loaded. At night, because there is no solar, the flow through the lines is very low. Now, as you heard me saying, then your system becomes capacitive and the voltages become too high, which is a risk. So what they do is they switch off some of these lines, which is then going to redirect the flow through some of the remaining lines, increase their loading, and therefore then again bring back the system to being less capacitive. I hope that answers the question.
Yeah, but just I want to add, in IEEE this is called 1547. In USA, you mentioned many times USA, Europe. So all the inverters that has this capability to go for positive Q to negative Q. It means
correct.
Reverse way as well. So if your system is more Q or more whatever is positive or negative, then your smart inverter automatically react on that. So it should not be the generator can see that much difference from positive to negative or something from reverse direction, because your smart inverter automatically take care of those things.
Yeah,
so
but
if your inverter is fixed, then it happens. But if your inverter is a smart inverter, it can control from, let's say, some voltage. It should control this. Otherwise, yes, you will have this issue. Yeah.
Absolutely. But the point, what I showed in the graph, those are measured at substation level, right? So if you have residential PV, Your residential PV is not going to control the voltage at substation level, right? It will control the voltage at the connection point, which is normally your terminal at home. But indeed, if you have large units which are connected to substation, of course, they should have that capability. And all grid codes, indeed, also in US, they are
No,
requiring.
in USA, in USA right now the rule is even in personal home rooftop, they should have a smart inverter. It should control the queue as well, not only the.
Yeah, but where is it?
Yes.
Where is it controlling the queue, Ahmed?
Yeah, because of the voltage.
No, but where?
Voltage
At which point? At which? What is the set?
At the connection point. At where it is
which connection point? Exactly, but not at the substation level, right?
Yes.
What I showed you here is the substation at 400 kilovolt. That's the measurement points.
But well, yeah. So we can discuss those things later. Okay, thank you.
Sure. Thank you for your question.
Vinay, we have 2 more questions in chat window. So.
Oh yes, an increased demand for harmonic. The first one is from Hassan. Are we anticipating an increased demand for harmonic power system studies in the future, as requested by utility companies for commercial and customer sites? APS stands for? I think it's a utility.
Arizona Power Supply.
Sorry? Arizona Power Supply.
Yep.
Oh, yeah. So I think this is a very, very good point. And the short answer is yes, there will be a massive increase in the demand for harmonic studies, not only for generation, but also for demand. You can see the NERC issued a report a few months ago saying that all these technical studies should be expanded to demand facilities as well. I know that generation connections are already, depending on the region, starting to provide and have to develop models that can look at harmonic assessments, but this is only going to increase, absolutely. And the reason why you don't see it in some regions like PG&E and SCE is that, you know, some utilities don't have that problem yet, right? Some utilities just don't have the problem yet, but it will absolutely come. It will absolutely come. Then there's another question on how to manage high rate of change of frequency in the grid and if power electronics interface devices can be of help. Absolutely. So this is the topic on grid forming, for example. Coach, you mentioned as well in the beginning, right? The grid forming control. So if you have a battery energy storage or renewable generation asset or HVDC, when you have grid forming control, your system is, your device is going to automatically and inherently act on changes in the frequency.
Yeah, thank you for responding to all of the questions. So yeah, if we consider like a grid forming converter technologies in the future, and then we can provide like a kind of virtual inertia to the grid, and then essentially the inertia is a function of rate of change of frequency. So if we use it, and we can provide more virtual inertia to the grid. So, but as the Vinay has already mentioned, so the technology is not yet matured, and then the many manufacturers propose their own strategy or methodologies, and probably the regulation will be needed in the future. And then US has already initiated. And then I heard that the European countries has already, the started regulating a portion of the technological aspects from the grid forming converters.
Correct.
And what is the latest status of this regulation regarding the grid forming converter in the EU?
So I think there is no EU level regulation as such yet, and that is not a bad thing, because I think at EU level regulation normally targets these performance of devices. It doesn't say you need to have grid forming control. It will say you need to have certain performance characteristics. Specific countries, specific utilities, on the other hand, they have started to come up with requiring grid forming behavior from certain assets, which is a good development. And I think in due time that will transfer to, let's say, an EU level legislation, I think. What NSUE did, they published a few years ago a wide a more wider overview of all the services that would fall under this, let's say, grid forming characteristics. That includes damping, that includes what you mentioned, the inertial response. So I think there are 7 or 8 characteristics that they mentioned to be part of that grid forming functionality.
Okay, so it depends on the country or each TSO in the
Yes, correct.
Okay.
Correct. For now, yes, but I think that, as mentioned, right, I think that will change in due time.
Okay, perfect. Yeah, so I think the time is ticking, and then also everyone in our region must be starving now. So I would like to close this webinar, just showing the future webinar schedule. So we have 2 forthcoming webinars. One is on April the 26th, which means Saturday. And then this is a sponsored by IEEE Hawaii section, not the Foothill section. The Foothill section is a co-sponsor this webinar. And then the next one after next is regarding the wide area monitoring system. This is a demonstration project in South Korea using a synchro waveform technology, like a more like high frequency sampling measurement devices. So the speaker will be Seung-gun Choi from South Korea. And then the webinar will be held on June the 12th, starting at 11 a.m. our time. Okay, so anyway, let's close this webinar, and then so the flyer will be uploaded in the footage section website, and then please rest of your day. And then again, Vinay, thank you for the excellent presentation today.
Thank you, and thank you for having me. Have a nice day all. Bye-bye.
Yeah, bye for now, everyone.
Thank you very much.
Yeah, thank you for joining us.